All right, greetings everyone. The purpose of this video is to go over section 2.5 from our OpenStax Calculus textbook. And so let's jump into it. So this section covers what we call the precise definition of a limit. So up to this point, we've talked about what a limit is, different ways to find a limit of a function. Now we're going to kind of dig into like the mathematics behind the scenes. So this is again kind of the like really formal definition of a limit from a mathematical standpoint. So what I'm going to do is go ahead and read it. You see it there at the top of the slide, and then I'll explain a little bit more about exactly what it means. So the precise definition of a limit says, let f of x, some function, be defined for all x not equal to a over an open interval containing a. Let L be some real number. Then basically the limit as x approaches a of that function of f of x equals the value L if, and this is where it gets a little complicated, for every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus a, which is less than delta, then the absolute value of f of x minus L is less than epsilon. Pretty straightforward, right? No, not so much. Okay, so first of all, I just want to point out, if you're not familiar with Greek letters, this little like e, lowercase e thing looking here, that's epsilon. This kind of like O with a tail on the top, that's delta. And the real key pieces of this definition are these things here, that if absolute value of x minus a is less than delta, then f of x minus L is less than epsilon. And actually, I shouldn't say that. It's this part's up here is important too. So what is this saying? Well, notice that the epsilon here has to do with this part of the definition down here that has f of x's minus L's less than epsilon. So what is it saying? Well, let's first of all look at this example down below. So we have this function square root of x minus 1. We have the blue line there. It's representing what the function looks like. And we're looking at the value x equals 5 and see that, first of all, the output of that function right there is 5. Is 2 from over here on the vertical axis. And that's also the limit as we approach 5 for this function, right? Because if we notice from the left, if we look at getting closer and closer to that point from the left, and from the right, it looks like we're getting closer and closer to that value 2 on the outputs. Okay, great. So what is the limit definition saying about that? Well, first of all, it says that if we choose epsilon and any epsilon value, which is basically a distance around this value 2 here. And so what do I mean by that? So basically, let's say that epsilon equals 0.1, okay? It means that if I go 0.1 in the up direction from that value 2, so basically up to 2.1, and then if I go down below that, so 0.1, which would be 1.9, basically, if I go for any value in between those, for this epsilon equals 0.1, there's going to exist some value delta, and I'll tell you right now, I can't draw delta very well. I just do an O with a little tail on the top like that, such that if a value is within delta of the x value down here, so we don't know what delta is, but basically if we go up an amount delta or down an amount delta, okay, so for this epsilon, there exists some delta that if we go in either direction, above or below the value 5, then the output values for all of the x values that fall within that particular interval, so all the output values we get up here, are going to be within epsilon or within this interval here. Okay. So again, that's kind of convoluted, so let me go over it again. So basically, again, we choose this value epsilon, and we know there's going to exist some delta, such that for all the values here that are within delta of the x value, again, meaning they're at most delta units away in each direction, their output values, the values we get up here, if we look at how they relate to the interval over here, their output values are going to be within that range of either epsilon above or epsilon below the output value, or sorry, the limit, what we're saying the limit value is. Okay, so again, clear as mud, right? Okay, so let's look at how we would actually calculate something like this, or how we could actually check that this definition holds for a particular function or a particular limit. Before we do that, though, first I need to show you a multiplication property of absolute values, because it's going to be important for us. So you may have seen this before or may not have. It's okay either way. But what this property says is if we have the absolute value of two values being multiplied, so here we're saying the absolute value of A times B, we can break that apart into the absolute value of the first thing times the absolute value of the second thing. Okay? And this holds actually for any number of values being multiplied within an absolute value. So if we have like absolute value of A times B times C times D times so on and so forth, we can break that up into the absolute value of the first times the absolute value of the second times the absolute value of the third, and so on and so forth. All right, so let's take a look at this limit definition in the context of a specific problem. So based on what we've learned before this section, you could probably check that the limit as x approaches -2 of 5x plus 3 equals -7. And this is one of those ones we can check real easily because -2 is in the domain of this function, so we can just plug it in for x there and we get -7, so we know that's the limit. Okay, but we want to prove this kind of using that precise definition of a limit. So notice that we're told to use the precise definition of a limit to find a suitable value or values for delta if we're given that epsilon equals 0.5. And remember, epsilon is that value around, or that distance around the output value or the limit value. Now, again, the definition says that if we're given an epsilon, there has to exist a delta, which means we have to find a delta for which all that other criteria is satisfied. And in fact, what we're looking for is whatever that value for delta is. And once we find it, then it has to be true that if the absolute value of x minus the value we're approaching, which is the -2 here, if that is less than delta, okay, again, whatever the delta value is, meaning that the values of x are within, they're delta above or delta below the value -2, then we know we're guaranteed that the absolute value of the function, the f of x minus the value L, which is the limit, is going to be less than the value of epsilon. Okay. And again, our goal here is to find a delta value. Now to do that, we're actually going to work backwards because we're trying to find this, but we're actually going to start at the end here and work backwards and use this absolute value to try to find the value for delta. So what is that going to look like? Well, first we're going to fill in information here in this inequality that we know. So for f of x, we can input the function from our limit. So 5x plus 3 minus the value L here is the actual limit value, so -7. Okay, and that all has to be less than the value for epsilon, which we're given over here, which is 0.5. Okay, and believe it or not, by doing this, we'll be able to find a suitable value for delta. Sorry, just going to clean that up a little bit there. Okay, so let's go ahead and do some simplifying within our absolute value. So I'm going to rewrite this as 5x, and then notice that we have a +3 and a -7. The minus minus there will make a plus. So this will become absolute value of 5x plus 10 being less than 0.5. And then notice that within the thing we have in the absolute value here, the 5x plus 10, both parts of that are divisible by 5, right? The 5x is divisible by 5, and the 10 is also divisible by 5. So what we can do, because of that, is we're actually going to factor out a 5 from that expression. So we're going to do absolute value of 5 times, factor out the 5 from each piece. So that'll give us x in the first part, positive 2 in the second part. So we have absolute value of 5 times x plus 2 is less than 0.5. And then notice now what we have inside the absolute value are two things being multiplied, right? We have a 5 here and an x plus 2 here. Those are being multiplied. And so we just talked on that previous slide about the multiplication property of absolute values. So we can go ahead and use that here. So we're going to break this apart into the absolute value of 5 times the absolute value of x plus 2. That's all going to be less than 0.5. Sorry, I'm going to have to move up here to keep working. Now the absolute value then 5 part, that part we can simplify, right? That's just the absolute value of a number. So absolute value of 5 is just 5. So it becomes 5 times the absolute value of x plus 2 is less than 0.5. And let's notice at this point that now inside the absolute value, we have something that looks real close to what's up here, right? X plus 2 and x minus negative 2 are actually the same thing, right? Because if we have x minus negative 2, we could make those minus minus a plus, and so that becomes x plus 2. So what we have in our absolute value here is actually the same as what we have in our absolute value up here. So what we want to do then is change this inequality so it looks like this one. And so we can do that simply by getting rid of the 5 next to the absolute value of x plus 2. And we can do that, remember, when we're solving inequalities, it works the same as when we're solving equations. So we can just go ahead and, sorry, I'm trying to find the right color. There we go. And divide both sides by 5. Okay. Cancel this out. And so then we end up with absolute value of x plus 2 is less than 0.5 divided by 5 is going to give us 0.1. Okay. And again, this matches with what we had up above, which was the x minus negative 2 being less than delta. So what that tells us is a suitable delta value here would be 0.1, which tells us that for all x values that are within a distance of 0.1 of the value we're approaching in our limit, the negative 2 here, their output values, their f of x values, are going to be within epsilon, which in this case our epsilon is 0.5, of that limit, -7. Okay. Now, one more thing about this example is notice that we have absolute value of x plus 2 is less than 0.1, okay, as the value of delta. Since it's less than, it also means we can choose smaller values. So our delta here, we've just shown that the value for delta of 0.1 will work, but a smaller value would also work. We could use 0.09, 0.08, 0.07. Any value smaller than 0.1 will also work. Okay, well, this is for a specific value of epsilon, right? We were told that epsilon equals 0.5 here. But what if we want to do this kind of more generally for any value of epsilon, right? So let's look at a example of that. So here, again, we're given that the limit as x approaches -9 of 1/3 x plus 9 equals 6. Again, we could double check this fairly easily since -9 is in the domain of this function. We could just plug it in there and we'd find that the limit is 6. And we're asked to use the precise definition of a limit to find a suitable value or values for delta that works for any arbitrary epsilon greater than 0. Now, if you've never seen this word arbitrary here, it just means any value for epsilon we could choose. And generally with these, or actually not generally, always when we're talking about the precise definition of a limit, our values for epsilon always have to be greater than 0. They basically have to be positive, right? And again, arbitrary means we could choose any value for epsilon. So we need to find a way to describe delta that would work for whatever value we choose for epsilon. So it could be +2, it could be 1,000,000, it could be 0.001, it could be pi, whatever we want it to be, okay? You might be thinking, well, that seems kind of crazy. Like, how are we going to be able to describe value for delta that will work for any value of epsilon? And the answer is I will show you. Okay, so we're going to approach this similar to the one that we, similar to the same way that we approached the last one. So we're going to remind ourselves that in our definition, it says that if the absolute value of x minus the value we're approaching, which is at -9, is less than delta, once we found delta, then it also has to be true that the absolute value of f of x minus L will be less than epsilon, right? Now, again, we don't know what epsilon is in this case, but we're just going to leave it as epsilon there. And just like with the last one, I'm going to fill in these values here. So for f of x, our formula here is 1/3 x plus 9 minus our value for L here is our limit, which is 6. And we're going to say that's less than epsilon. Okay. And then we can go ahead and simplify again. So within the absolute value here, we'd have 1/3 x, we have the +9, the -6, that'll give us a +3, less than epsilon. All right, and you may remember from the previous one that at this point we were able to factor the thing inside the absolute value, which this may not look like that since there's not a number that specifically describe or divides both 1/3 and +3. However, we can still go ahead and factor this one. And so we're going to do that by just factoring out the leading coefficient there with the x, so the 1/3. So go ahead and factor out 1/3. When I do that, the first term there just becomes x. To figure out what the second term becomes, remember that when you're factoring, it's like you're dividing, right? So what I would need to do is do 3 divided by 1/3, which if we do that, we can make this 3/1. We're dividing with fractions. Remember, we change the division and multiplication, flip the second fraction, so it becomes 3/1. Multiply, we get 9/1, or just 9. So inside the parentheses here, we'll have x plus 9. And then we have this whole thing less than epsilon. All right. Okay, and then again, just like the previous one, notice that what we've ended up with here are two things being multiplied within the absolute value. So we know that this means that we can go ahead and break that apart into the absolute value of two things separately. So this would be the absolute value of 1/3 times the absolute value of x plus 9, all less than epsilon. Absolute value of 1/3 is just going to be 1/3. So we have 1/3 times the absolute value of x plus 9, less than epsilon. And notice again, just like on the previous one, what we have inside the absolute value here, that x plus 9, is very similar to what's inside the absolute value up here. So the x minus -9, that would make x plus 9. So we're going to go ahead again and isolate that absolute value of x plus 9. We can do that since we're multiplying by 1/3 here. We can multiply by 3 on both sides. That'll cancel out the 1/3 on the left. And so we're left with absolute value of x plus 9 is less than on the left-hand side, or sorry, the right-hand side, and we do epsilon times 3, we can just write that as 3 epsilon. And again, recall that this lines up with what we had up there, which was the x minus -9 is less than delta. And so we see in this case that delta would be equal to 3 epsilon. Okay, so what this tells us is that for any value epsilon that we choose for this particular limit, If we just choose our delta value to be equal to 3 times whatever that value is, then we'll have found our suitable delta to satisfy the limit definition, or sorry, the precise definition of our limit. Okay, so that's a lot of information. I would suggest that perhaps you go back and rewatch parts of this video to try to get a deeper understanding of it, and or go ahead and check out the section 2.5 in the textbook for more information. All right, that's it for now. Thank you for watching.